Hello class, this is Mr. Hunter and this is your motion graph notes. So with the previous notes as well as in class, we've been talking about the differences between distance, displacement, speed and velocity, as well as acceleration. And as I mentioned in class, physics is just math in a dress. And so everything you've learned in your previous math classes still applies here. So if you're looking on the front page, you should be looking at the motion of the object, and you should be looking at a position time graph. Now, position, as you've seen from the Vector Treasure Hunt lab, is really talking about displacement. The reason why it's called displacement here, even though we still refer to it as a distance time graph or position time graph or displacement, almost one and the same, is because it's relative to the origin. So for example, if I'm, according to what this says right here, I am 5 meters away from my origin. And as we graph the object's motion over time, so it's the really cool thing with these graphs is you can look at a graph and you can actually tell, depending on the type of the motion, whether it's velocity, displacement, aka position, or acceleration, you can actually tell what the object is doing by reading the graph. So for example, if over a span of a few seconds, the graph isn't doing anything, mathematically I'd say, hey, what is that slope? And hopefully you should be able to pause and tell me that that slope, or it has no slope, it has a zero slope because it's a flat line. So in this case, if I'm standing there at 5 meters, the question is, do I move? And according to this graph, I don't move. So the motion of the object is the object is standing still. There is no displacement according to where they started from, 0 being the origin. So how can we confirm that? So once again, as I scroll down, it says, what is the object's velocity? And the object's velocity is, as you stated, it's a 0 slope. The object's not moving, so the object's velocity has to be 0 meters per second. It doesn't move. And that can be confirmed, once again, mathematically by the slope equation. Now, this is review. You should hopefully remember how to find the slope of a line, which you guys know it as rise over run, which is your change in the y position over your change in x position. So in this case, let's say when you take a slope, you have to pick 2 points on the line. So let's pick 1 and 5, and let's pick 4 and 5, right? So my 2 points are 1 and 5 and 4 and 5. So when I calculate it, I have 5 minus 5, and you'll have to forgive me, I did not do units. So 5 meters, 4 seconds, because our x-axis is time is in seconds, our y-axis is distance. So I have 5 meters minus 5 meters over 4 seconds minus 1 second, and what I really get is 0 meters divided by 3 seconds, right? But anything, well, numerator is 0, so it comes to 0 meters per second. I also want you to notice that if you notice how I put the units in, then meters is on the top because that's the rise, seconds is on the bottom, and the unit for that is meters per second, which we know is velocity. So we can tell that a distance time graph, so a d versus t graph, the slope equals the object's velocity. That's something you need to know. You need to know that if you're looking at a position time graph, the slope of that graph is velocity. It also can be confirmed, as we stated, by doing the rise over run of the actual graph. So let's scoot down. So now we have the motion of the object, and now it doesn't look like it's standing still. It's not a straight line. In math, you say that this is a constant slope, which means that any point on that line is going to be one value. So the motion would be constant velocity. And the reason why I can say velocity, because you might say, Mr. Hunter, why is it not speed? The reason why I could say velocity is because the slope is in the positive direction. The number is positive, so therefore that's my direction. My direction is in the positive or to the right, and we can see that because it's a positive slope. So once again, the slope tells us velocity, so the slope equals velocity. And if you figure out the slope, that will tell you that the velocity that it's moving at. So in this case, I have 5 meters and 5 meters, and so we're actually going to figure out the object's velocity by using the slope. So once again, we pick 2 points. Let's just pick the origin. We have 0, 0, and then we have 5, 5. And once again, I didn't use units, which I'll get to in a second, but I'm just reviewing how to do the slope. That should be y1, x2, y2. So this should be familiar for you, how to find a slope of a line. You guys should technically be able to do that by your sleep now, because you've done this so many times in other classes. So it's my delta y over my delta x. So that's x is seconds, y is meters. So I have 5 meters minus 0 meters over 0 seconds, 5 seconds minus 0 seconds, which leaves me with 5 meters divided by 5 seconds equals 1 meter per second. So we know that that line or that object is moving at a constant velocity of 1 meter per second because we can figure out the slope. Please remember, slope of a displacement time graph is velocity. Okay, so head over to the second page. Flip over to the back of that sheet I gave you. Now we have a velocity time graph. This says, hey, this is the object's actual velocity. So I can ask you kind of a few questions here. The easiest question I can ask you is, hey, at 5 seconds, how fast is the object moving? And hopefully you could just look at this graph and you're like, oh, it's a velocity time graph. At 5 seconds, it's moving at 5 meters per second. So once again, it has, as we could see from before, no slope, but the object is still moving. So the motion is still constant velocity. Why? Because this is a velocity time graph. We're not looking at displacement anymore. We're actually looking at velocity because that's what's on the y-axis. So it's a constant velocity of 5 meters per second. Now, we're asked for what is the object's acceleration. If the slope of a displacement time graph tells you velocity, well, the slope of a velocity versus time graph tells you acceleration. And I'll show that to you mathematically. So we got to find the slope. But you're already going to tell me what the slope is, right? You know that the slope is 0, and if you remember the units, 0 meters per second squared. But once again, let's just do the sanity check. Delta y over delta x is going to equal 5 minus 5 over, am I doing it right? Blah, 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 blah. Yep, it's going to be 5 over 5 minus, we could take it at any time, so we could say like 5 minus 4 seconds because it's always the same. And so once again, we get 0 meters per second divided by 1 second. So just like I showed you in class, we have meters, 0 meters per second squared. Now, just warning you, this is probably going to go over a little 10 minutes. I'm at 9 right now. Okay, so now we move down to the last graph, which this says, hey, it's a velocity time graph. What is the motion of the object? So as we just stated, the slope of that line is acceleration. And as we know from math, it's a constant slope, so the acceleration has to be a constant value. And just because I worked in math, so we would say that this is a constant acceleration. And because of the way I set up the graph, the constant acceleration is going to be at 1 meters per second squared. And we can see that because we could pick the time of 5 seconds at 5 meters per second. And we pick another point, which is, we'll just say 0 seconds at 0 meters per second. And it's going to be the same math as before, so I'm just going to not waste time writing over the same equation, but you're going to get a unit of 1 meter per second squared. So the real question is, and here's what the cool thing is, you can actually find the distance traveled from a velocity time graph, and that's very critical. You really need to remember that. So remember, on a velocity time graph, the slope tells you acceleration. The area under the curve actually tells you the distance traveled. So if you ever have a velocity time graph and they say, hey, in 5 seconds, how far did the object travel? Then you actually would need to figure that out. And you figure that out by taking the area under the curve. So you would actually have to find that area. What area that makes? Well, that's a triangle, and I know the equation for a triangle is area equals my base times my height divided by 2. So my height is 5 meters per second. My base is 5 seconds. So let's write down those values. So my height equals 5 meters per second. My base equals 5 seconds. And so I plug it into the equation, and I get 5 meters per second multiplied by 5 seconds, all divided by 2. Notice the seconds cancel out, right? So that means I have 25 meters over 2, which gives me 12 and a half meters. So the distance that I traveled in that time, according to this graph, is 12 and a half meters. It's really important that you remember that on a velocity time graph, the area under the curve is distance and the slope is acceleration. Now here's the thing. Notice I never used average velocity equals displacement over time. I never used acceleration equals change in velocity over time. Only use slope and area. So sorry, trying to speak and write. Only use slope and area on graphs. Do not ever use the equations because they don't work. There's one exception to the rule, and I'm not even going to tell you it because I don't want you to use it at all. Secondly, flip back to the front of the page. So we talked about acceleration. Well, I'm going to show you this mathematically later because I've run out of time. But acceleration on a displacement time graph looks like this. And I am well over my 10 minutes. So I will stop it here, and we will talk later about this. I will be checking this in the morning.